Hi, this is a little fill-in lecture that I'm putting together to cover the 5 slides that somehow got eliminated from the YouTube video that I made for adaptive immunity. We got as far as starting to talk about this slide, the primary versus secondary responses. That just means how your system responds if it's the first time it encounters an invader, an antigen, compared to after you've already done it once. The first time your initial exposure to, let's say, a virus or a bacterium or something, they'll have antigens on their surface. Your complement system will try to fight them some. It'll send out some signals, and some neutrophils will start showing up. They have a hard time recognizing the bad guys unless they kind of run into them. So their initial response is not all that robust. And then they send out the signals, cytokines that go back to the rest of your immune system, to your lymphatic system. And your B cells start to mature in response to this. With help from helper T cells, they mature into plasma cells that can make an antibody for that particular antigen. They release the antibodies, it sticks to the bad guys, and now your neutrophils attack it very effectively. They're attracted right to it and have a place to attack. And so that takes about a week. That's why if you get the flu or a cold or something, you're sick for a while before you get better. It takes your immune system that long to ramp up all of the tools that it needs to kill off the bad guys. And remember that the reason, even if you've had the flu before, if you get the flu the next year, it's a different flu. And so you may have a little bit of residual immunity from having had the flu 2 or 3 times in your life, but it won't help very much. The same with the common cold. I mean, the common cold isn't going to kill you. You've had colds before, but they mutate so rapidly that you always have new antigens that haven't been identified yet. But if it's the same one, if you've had the flu one time in a season, it's very unlikely you'll get that same flu again. And certainly things like, smallpox, if somebody survives smallpox, they have memory cells and they'll never get smallpox again. And vaccines, a vaccine sets you up for success by doing all this preliminary work first, so you already have the plasma cells there, with the ability to make the antibody that you need, so the instant it shows up, the antibodies stick to it and you attack it. It doesn't keep you from getting the infection, but it kills it so quickly that you either don't get sick at all or you don't get very sick. And so that's, what this whole process is about. So a secondary response, if you've already had that virus, or if you've had a vaccine for that virus, it's very rapid. You already have a lot of memory cells, the B plasma cells, and so they produce them so quickly, the antibodies so quickly, that often you don't even know you were infected. Now, there are occasionally super antigens. They activate more than just one kind of lymphocyte. They activate a lot of different lymphocytes. They act like multiple different antigens. So different kind of cells get activated, and it can produce an excessive immune response. COVID, the coronavirus that we're dealing with, is similar. It's like that in a way. People, they get the virus, they get sick, and about 4 or 5 days later, they start to get better, and they go home, and then they get really sick and die from it because their immune system is becoming overreactive and producing what they call the cytokine storm, and produces all kinds of, deadly type of responses, shock, low blood pressure, high fevers, and the like. Talk about a couple of other kinds of cells. We have the C-type cytotoxic. That means toxic to cells. TC, or T cytotoxic cell, is a particular kind of T cell. Now we're going to talk about like a couple kinds of Ts. We have helper Ts, we have regulatory Ts. The helpers make the immune system, B cells work more. Regulatories suppress them. You have natural killer Ts that they glom onto something and inject it with a toxin. These cytotoxic T cells, though, really have an interesting plan, and that is they will make contact with the virus or the bacterium, and they secrete something called like perforin, which perforates the membrane of the bad guy, and then it allows granzymes, which cause apoptosis, to enter. And if they get into these cells, they'll cause them to self-destruct. So here's the natural killers down there, a direct cytotoxin. The T cytotoxic, they've awfully similar name, but they cause them to self-destruct. And what's good about this is this can work on your own cells. If you have a cell that is so sick, or even a cancer cell or something that needs to be killed to keep you alive, it doesn't have an antigen on the surface that you'll recognize and make antibodies against it. You won't make antibodies against your own cells. But if you detect cells that need to be killed and you can cause them to apoptosis themselves, then you can cause them to be gone. So here we have, he's binding to this bad guy. He puts the perforin in here, and then connects around to them and puts in the apoptotic enzymes that cause those to explode and disintegrate themselves. Here we have a natural killer cell over here, which is simply binding to a something on the surface. This would be for like an invading cell that doesn't belong to you. Or if your own cell was so sick that it created an abnormal change on the surface that could be recognized. And so this cell would recognize this as a cell that has to be killed. Then it just injects a toxin. So the TC, the cytotoxic T, uses the apoptosis process, and the natural killer injects a cytotoxin just to kill the cell directly, like injecting it with Clorox. So here we talk again, the natural killer. It's a different kind of cytotoxic cell, but they named them separately because they work differently. Direct contact, directly injecting cytotoxins. And I mentioned the regulatory T cells. We talked about helpers. Regulatory Ts and helper Ts are actually part of the same category, but one helps the B cell mature and start making antibodies. The regulatory T prevents it from doing that so much. It's to keep it balanced so you don't have an overreaction of your immune system. So, multiple kinds of T cells. Natural killers, stick to the cell, inject it with poison. Cytotoxic Ts, perforate the membrane and put in apoptosis enzymes that will cause the cell to self-destruct on its own. Helper Ts make your B cells work. Regulatory Ts suppress the effect of B cells. And here is a recap slide. B lymphocytes. Most of them are created in your bone marrow. The only one that I know of for sure is made somewhere else. Your cytotoxic Ts are made in the thymus, and then they enter the lymphatic system. generally speaking, you can say it's your bone marrow that makes white and red blood cells. B lymphocytes enter the lymphatic system, and then when they are signaled by the binding of an antigen or by a cytokine that has bound to an antigen binding invader, and with the help from the helper Ts, they cause them to become mature plasma cells for making antibodies. T cytotoxic cells enter the lymphatic system, and when they bind an antigen, they become attack cells that perforate the membrane, apoptosis. Natural killers respond to the antigen on the invaders and kill by injecting poison. And then those T regulatories that will reduce the effects on your B cells to keep them from overwhelming you. So that's a pretty good roundup. And this was the slide we finished on before it popped back on partway through this one, talking about pediatric immunity. As a fetus, you're protected by your mother's immune system. When you're born, you're on your own. Okay, so when you're first born, though, human neonates are pretty immature. The lungs are not very developed. They may not produce enough surfactant. Your immune system, your thermoregulatory system isn't very good. It's hard to keep, or you have to be sure that you keep your baby at the right temperature because they don't thermoregulate well. And their immune system is weak. In particular, a couple of, including the immunoglobulin Gs, which are so important, not only they don't have very many of their own, but their B cells aren't capable of turning into plasma cells and making these for a while. So neonates are susceptible to infections, viruses. You talk about the babies and young children who get COVID and wind up with this overall inflammatory response and so forth. Their systems aren't really good at handling that. So right about the time the child is being born, maternal antibodies go through the roof. Mom makes a whole bunch of them so that they can move into the baby and provide protection for a while before the baby's system catches up. Also, breastfeeding, initial colostrum and initial milk for the first, breastfeeding definitely transmits more of mom's antibodies into the baby. So it's likely to be protected longer after childbirth before it starts making its own. Here we have the baby's circulation, the maternal circulation out here. You actually, by endocytosis, take in antibodies from mom up until the time of childbirth. And so you can see as you're approaching childbirth, mom's antibody G, especially the IgG that the baby is incapable of making. So you're not making any at birth as a baby. So maternal IgG goes way up, a lot of it goes into the baby, and for a couple of months, a few months, there's enough of mom still in there to protect the baby until the baby's own immune system can pick up the slack and bring it up to where it needs to be. And I think you're going to be okay with the rest of the original PowerPoint on this one. All right, take care.